All right, people. So we are going to start today with magnetic fields due to electric current, and in this chapter, we are going to primarily study how electromagnetism actually works. Okay, so there are a lot of things to cover. Understand. Uh, First, we have to understand the derivations, then the problems that are associated with it, and obviously we will then look into the problems that have been frequently asked at board level and at a level of IIT or a NEET or a CET. Okay, so let's start with this magnetic field is due to electric current. So till now, what have we learned? We have learned about motion, we have learned about electrostatics, and we have learned about current electricity. This is the basic expectation before we happen to start with this chapter. Okay. Now we are certainly today going to cover what is magnetic field, what is Biot-Savart's law, and magnetic field due to current carrying finite wire. Okay. So first of all, we need to understand what was the experiment that was involved by which we were able to conclude that any current carrying conductor basically has a magnetic field around it. Okay. So the experiment was actually performed by Oersted, and we have read this in previous classes and standards as well. The Oersted experiment is quite famous, in which there was actually a there is actually a wire connection and there is a circuit, and we have placed a magnetic needle close to this. So the moment the current is switched on, or you will see that there is a certain amount of deflection produced in the magnetic needle. And if you happen to reverse the potentials, let's say now this is plus and this is minus, you will see deflection in a certain direction. If you change the potentials, make this minus and make this as plus, you will see that the magnetic needle deflects itself in an opposite direction. So he did an experiment in which he placed a magnetic compass within a current carrying loop. He observed that the magnetic compass shows deflection when the current is passed through the loop, supporting the fact that moving charges induce magnetic field. So obviously any charge which is in motion will induce magnetic field. Okay. The deflection changes its direction. So if the current is flowing in this direction, this magnetic needle is supposedly going to show a deflection in a particular direction. If the current moves in this direction, the magnetic needle will show a deflection in the opposite direction. Okay. So it's a very simple thing. So do all current carrying conductors have a magnetic field around them? The answer is yes. All your circuits in which current is flowing through a conductor will have a magnetic field around them. Okay. Uh, Especially when we have concealed wirings. These days, the wirings in most of the houses is concealed. It goes inside the walls. And if there happens to be a fault, okay, by placing a magnetic needle, you can identify where the fault is. Okay. So if there is a short circuit or if there is something which has occurred as a fault, we can actually place a magnetic needle and identify the fault. Okay. So a current carrying conductor actually behaves like a magnet. So what we need to understand here is the direction of the magnetic field. The direction of the magnetic field, we have to just understand the right hand thumb rule. So if this is the current carrying conductor, obviously the magnetic field would be encircling. The encircling of the fingers will resemble the magnetic field. So let's say this is the current carrying conductor, and this is like placed like this. So here we have the magnetic field like this. So one is entering and the other one is leaving. So if I am considering this board, one is leaving and the one is entering. So the one that is leaving will have be represented by this, and the one that is entering will be represented by this. Okay. So this is a current carrying conductor. A current carrying conductor behaves like a magnet. The orientation of the magnetic field around the current carrying conductor is like circular rings around the conductor, and the strength of the magnetic field is larger in the vicinity of the conductor. So this particular signal is for current going inside the board or the plane of your paper in which you are writing. And this particular symbol, that is dot, actually is the magnetic field towards you. This is magnetic field inside the board or the plane of the paper. This is magnetic field towards you or coming outside. Okay. So now obviously, the more closer you are to the current carrying conductor, the stronger will be the magnetic field. Okay. So sign convention, this is basically coming out of the plane and this is going into the plane. This is coming out of the plane and this is going into the plane. Okay, let's move ahead with the next topic here. Now, understand what is current. Current is moving charges. So, if we have a conductor, or rather anything in which the charges are stationary, they are not moving, will there be a magnetic field? So the answer is no. Until and unless the there is, see, when there is a charge that is moving, when a charge is moving, only then will it produce a magnetic field around it. So now what happens is, if you keep a charge in an already existing magnetic field, let's say the charge is stationary and there is a magnetic field that exists, will the charge experience a force? No. But if you happen to move the charge, it will experience a force. Why? Because as soon as the charge moves, it creates a magnetic field of its own. And this magnetic field will come into clash with the external magnetic field or support it. But then it is going to experience a force. So when there is an external magnetic field and a charge is placed, which is at rest in that external magnetic field, the charge is going to experience no force at all. But if the charge is made to move with a certain velocity, then definitely it will experience a force, because moving charges will have their own magnetic field. And this magnetic field will generally either support the external magnetic field, or maybe at an angle with the magnetic field, or maybe at a clash with the external magnetic field. Then it's going to experience a force. So magnetic field does not exert any force on the charge which is at rest. It only starts applying force when the charge starts moving. So the charge starts moving, then it will experience a force. Okay. Okay, let's move on. So we will now talk about Biot-Savart's law. So what is Biot-Savart's law? Biot-Savart's law is basically applicable to a current carrying conductor, and we can derive this for finite as well as for infinite length. So what we need to understand is that there is a point, there is a current carrying conductor, certain amount of current is passing through this conductor. There is a point which is at a distance r from the conductor. In order to derive this, we have picked up a very small infinitesimal part of this length and we call it as dl. Now this dl, we know that doesn't have current is not a vector. Current is not a vector, obviously, but the direction of the current is taken as dl. Okay, so dl we have taken as a vector. What is this length? The length has been taken in the direction of the current. We can take the length this way and this way, but in this case, or rather in all the cases of all derivations throughout this chapter, we will take this. So this is called the current element, IDL. Okay, so DL is basically an infinitesimal wire segment having direction same as the current. So obviously length is also not a vector here, but we have forcibly taken it as a vector, because in physics, obviously we are talking about here, what we are talking about here is the magnetic field, which is a vector. And ideally the magnetic field will depend upon the length. Now obviously it will depend upon the current, and current is not a vector. So where do we get the vector from? So the vector is basically this dl. Dl is basically the vector segment. So dl means the dl means a very small portion of the wire, and the direction here is in the direction of the current. Okay, so position vector. So let's say we have basically a point and r happens to be the position vector making an angle. Very important. Many a times students get confused that maybe this angle is theta. No, we are talking about this angle, which is theta. So this infinitesimal part dl is making an angle theta with the point P, wherein we need to find the magnetic field. Okay, so uh, so r is the position vector of the point where we need to measure the magnetic field. dB is the magnitude of the magnetic field at a point P. So let's say dB is basically what? So here dB is the magnitude. Now what does Biot-Savart's law state? dB is directly proportional to I. So dB is directly proportional to the magnitude of the current that flows. This magnetic field will be directly proportional to the magnitude. dB will be inversely proportional to R square. dB will be proportional to dl. dB will be proportional to dl, and dB is proportional to sine theta. So all these are basically proportionalities. dB is proportional to the magnetic field which exists here, the dB portion, this is directly proportional to the amount of current that is being carried. It is inversely proportional to the square of the distance. The inverse square law is applicable for all non-contact forces. So obviously magnetic field and magnetism is a non-contact force. So the inverse square law will be by default applicable here. Okay. dB is directly proportional to dl. See how is this proportional? The more is the length of this dl, obviously the more the current will be. So obviously it will be directly proportional to dl. And dB is directly proportional to sine theta as well. That is Biot-Savart's law. If you combine all this, so obviously this will be dB proportional to I dl sine theta upon r square. Now in order to make it equal, what we do here is mu naught by 4 pi I dl sine theta upon r square. This mu naught by 4 pi is basically the constant that we have added, where mu naught is basically permeability of the medium. This is permeability of the medium. Okay. So if we happen to look at the scalar format, this will be dB is equal to mu naught by 4 pi I dl sine theta upon r square. That is the scalar form. Now, if we happen to change it to a vector form, so let's say we multiply this by r and this by r. So what do we get? So it will be dB mu naught by 4 pi, okay, I dl into r. So obviously dl is basically a vector. If we are having a vector representation, dl into r sine theta, let's say dl into r sine theta upon this would be r cube. So obviously dl r sine theta is nothing but a vector product of dl and r. So here we can write mu naught by 4 pi I dl into r upon r cube. I dl into r upon r cube. Okay. So this will be the vector representation. So if we are talking about, so this will be the vector representation. dB is equal to mu naught by 4 pi I dl into r by r cube. This is going to be the vector format. Okay. Now, obviously unit will be what? Newton amperes, Newton per ampere per meter. This will be basically the unit, or Tesla. This is the unit of magnetic field, dB. Okay. dB is the magnetic field intensity or magnetic field. Mu naught is permeability of free space. The value of, we always have to ensure that in all our numericals, we keep it this way, because this is going to directly give us 10 raised to minus 7 Newton per ampere square. Or we can say mu naught is equal to 4 pi into 10 raised to minus 7. Okay. Now the direction of magnetic field can be obtained by right hand palm rule. For example, here in this case, let's say, oh, okay. So here in this case, what will be the direction of magnetic field? The current is going like this. So this is going inside the paper. So this will be the direction of magnetic field, inside the paper or inside the board. Okay. So this is how we will apply the formula as well as determine the magnetic field that is there. Okay. So now let's talk about a situation wherein we have a current carrying conductor and we have 2 points on the opposite ends. What would be the magnetic field? So very simply, the magnetic field would be the same, that is mu naught by 4 pi I dl sine theta, because this is theta, okay, upon r square. For this one it will be mu naught by 4 pi I dl sine theta dash by r square. But in this case, understand, the so this is, the current is going like this. Encircling of fingers represents the magnetic field. So the magnetic field is going inside the paper. In this situation, the current is going like this. So if I happen to be at this point, for me the current is going like this. So the current is going like this. I am at this point. This is the wire. So encircling of fingers points this way. So the magnetic field is towards you. The magnetic field is towards you. Here the magnetic field is inside the paper. So to find the direction of the magnetic field, place your right hand palm along the current element and your fingers. Direction of your thumb will give you the direction of magnetic field. We can also use the right hand grip rule to find the direction of the magnetic field. This rule has been discussed. So we will basically see what is the direction of the magnetic field. So encircling of fingers, Now in this case, if you see, this is going inside the board, this is coming outside the board. So here it is towards you and here it is away from you. So point your thumb in the direction of the current's flow and curl your fingers. The direction of your fingers will mirror the curl direction of the induced magnetic field. Induced magnetic field means the magnetic field which has been induced due to the current that is flowing through the conductor. So for every conductor, you will have a magnetic field that is induced. Okay, let's move on. So here it is the oyster's experiment. What we have done here is we have given a connection to a battery. This is a wire which is going through a piece board, and on these piece board, what we have done is uh, we have placed iron fillings or any magnetic substance in a powdered format. So we will see the moment we happen to pass current, the iron fillings arrange themselves. In the same way here as well, radially they will arrange themselves. But in this case, the current is flowing. Notice the current is flowing this way. So obviously the magnetic field will be like this, encircling of fingers. This is representing the magnetic field. In this case, the current is flowing from positive to negative. So in this case, the magnetic field will be like this. Okay. So notice that as soon as we have changed the direction of current, the direction of magnetic field gets changed. So the moment we change the direction of the current, the direction of the magnetic field also changes. So let's call for a derivation here. Magnetic field due to a straight current carrying finite wire. Okay. So here let's understand. This is basically a wire connection. There is a point P. Okay. Now what we have done is we have taken a small length dl. The current obviously is flowing in this direction. Now the dl angle with this point, if I look at this, the point is making an angle of theta. The point is making an angle of theta with dl segment. The infinitesimal segment which has been taken, the point P is making an angle theta with it. Let's say the top of the wire is this and this is the bottom. So the point P is making with the extreme end B an angle of phi 2 and with the extreme end A an angle of phi 1. Okay. Now what we need to understand is that this is basically A and this is L. So the segment DL is at a distance L and this is basically A. Okay. So if we happen to basically find out what will be the magnetic field due to this portion, what we need to find out is what is the magnetic field at the point P due to this entire current, due to this entire current carrying conductor. But if we happen to put it, so what we need to do is basically integrate dl dl dl, all these dls, if we happen to add, the magnetic field that we will get here will be the total magnetic field. Okay, so let's do this here. So dB will be equal to mu naught by 4 pi I dl sine theta by r square. So this is the formula, mu naught by 4 pi I dl sine theta. Now what is sine theta? Theta here is what? Pi by 2 minus theta. So this will be sine 90 minus theta upon r square. So obviously here dB, see, understand, this is a triangle which is having 90 degrees. Here it is theta. So obviously this angle will be 90 minus theta. So dB will be mu naught by 4 pi. We are just following the Bio-Savart law that we have just studied. So this will be I dl sine 90 minus theta. Sine 90 minus theta upon r square. So this gives how much? Mu naught by 4 pi I dl cos theta, I dl cos theta upon r square. So this will be dB. Okay. All right. Now what we have to do is basically integrate. So integrating means all these segments of dl being added right from this extreme point to this one. Okay. So dB will be equal to mu naught by 4 pi I dl cos theta by r square. This is absolutely clear. Now about the angles, understand this. Here one angle is below and one angle is above. So look at the direction of this angle. Both are in opposite directions. So if we happen to take this as negative, obviously this has to be taken as positive, or vice versa. If we take this angle as positive, this has to be taken as negative. See, recall in quadrant movement for ratio of trigonometric angles, we generally tend to move in a clockwise direction. When we move in a clockwise direction, the angles are taken positively. When we move in an anti-clockwise direction, the angles are taken negatively. Okay. So the point A and B make an angle phi 1 and phi 2 with respect to the perpendicular line that has been drawn from the point P. But notice the direction of measurement of the angle. They are opposite to each other and hence they are written. So since the angles are opposite to each other, see, this angle is going in this direction, this angle is going in this direction. Now Here we have a cos theta factor. So obviously cos theta will depend upon the angle. So here we have minus phi 2 and here we have phi 1. Okay. So if we happen to integrate this, what do we get? So dB integration will give you obviously the magnetic field mu naught by 4 pi, mu naught by 4 pi r square, mu naught by 4 pi. Now r square has to be basically dealt with. Okay. So phi 1 to minus phi 2 mu naught by 4 pi, this will obviously come out. I will also come out. Now we will have to see about the other factors. So dB will be equal to this much. Okay. Now let's say this is a little simpler diagram here. This angle is theta. Obviously this distance is a. This distance is L. The length of this current element that we have taken, infinitesimal segment that we have taken, is dl. Okay, so now we can say that cos theta, look at this triangle, cos theta, this is base upon hypotenuse, that is a by r. So if we happen to do, so here we have r square rather. So cos theta is basically equal to a by r. So obviously r will be equal to a by cos theta. If we happen to square both sides, r square will be equal to a square by cos square theta. So this r square can be written as a square by cos square theta. Again, here we have, if we consider this L and this is A, so this is theta. So tan theta can be written as perpendicular upon base, that is L by A. So L can be written as A tan theta. See, the thing that we are trying to do here is, we have a dl, we have an L, so we have to bring all this to theta terms. Okay, so L, so if we see in this entire integration, we know that this segment will go out being a constant. We know that this segment will also go out being a constant. But what about dl and r square? Are they constants? No, they are variable, because you are going right from here to here. Cos theta is variable and r square is also variable. R square is basically the distance, so it will change when we move from here to here. Anything which is variable has to be considered under integration. Now we have to bring all these three in the same platform. That is the basic perspective. Okay. So all these three are different. DL is different, cos theta is different, and r square is different. But we have to integrate them because they are not constants. They are changing. DL is changing right from here to here. The value of theta is changing right from here to here. And the value of r, which is the position vector, that is also changing from here to here. So all of this has to be integrated. We put the mu naught by 4 pi outside. So here are certain things in which we are basically trying to convert. So here we have managed to convert r square in terms of theta. See, we will try to convert r in terms of theta, and we will try to convert dl in terms of theta as well, so that we are getting to a common platform during integration. Integration is a complex process. Differentiation is a little easier process. We can have different factors in differentiation, but in integration, we have to bring them all on a common platform. Okay. Now, so obviously tan theta is equal to this, dl is equal to, now if I happen to, so L is equal to tan theta, A tan theta. If I happen to differentiate this with respect to theta, this will be dl by d theta is equal to a d by d theta of tan theta. That gives you how much? A sec square theta. A sec square theta. So dl can be written as a sec square theta d theta. Okay. So in place of dl, we write a sec square theta. In place of cos theta, we write cos theta. So this is a sec square theta d theta, and in place of r square, we write a square cos square theta. Now this can be written as a square sec square theta. So what do we get here? One a gets cancelled with one a. The entire sec square theta gets cancelled with sec square theta. So we can bring the mu naught by 4 pi I by a outside, because a is a constant. This perpendicular distance of this point from this length of wire is going to be constant. So we can put this outside. Inside it will be minus phi 2 to phi 1. And what about d theta cos theta? So here what do we have here? This will be cos theta d theta. Now we know that for cos theta integration, d by d of sine theta is equal to cos theta. So we will get sine phi 1 minus sine phi 2, because we have a minus sign phi 2. So this integration is going to give us what? This integration is going to give us what? So this will be mu naught by 4 pi I by a. This will be sine theta between the limits of phi 1 and minus phi 2. So this will be mu naught I by 4 pi a. This will be sine phi 1 minus sine phi 2. So that gives you mu naught I by 4 pi a sine phi 1 plus sine phi 2. Sine phi 1 plus sine phi 2. Making sense? Okay, okay, okay. So this will be the magnetic field. P is equal to mu naught by 4 pi I by a sine phi 1 plus sine phi 2. This is simple. We are basically cancelling this. All we get is the integration of cos theta d theta. Obviously, I is a constant and this perpendicular distance is a constant. So they will come out of integration. Anything which is a constant comes out of the integrating terms. So sine theta, this will be sine pi 1 minus sine pi 2. We know that sine minus theta is equal to minus sine theta. Only cos has the capability of dissolving a minus. So cos minus theta is cos theta. Rest all other fraction, all other trigonometrical equations will not be able to dissolve a minus. So obviously this will be coming out and this is the final result. Okay. So now let's say we take a situation in which there is a wire and there is a point here on the axis of the wire. The current is flowing like this. Okay. So just by applying this, so here we have dB is equal to mu naught I dl into R by RQ. Now let's say mu naught by 4 pi, current is I, dl into R. So dl into, now what is this? This is basically a vector product. So this will be dl into R and sine of 0. Sine of 0. So that will be 0. So the entire thing will become 0. Now if we happen to keep a point here, if we, let's say, okay, if we keep the point here, what will happen? The dl is in this direction and the point is in this direction. So here the dl and basically r, the distance, are having an angle of 180 degree with them. This will be sine 180, which is 0. In this case, the angle between L and dr. So what has happened is I have taken the point here, but in this you can see that the current has been changed here. So obviously the point is this side. It means the same thing. Okay. So whether we are keeping a point this side or this side, if it happens to be on the axis of the current carrying conductor, if it is in the direction of the current, the point, then the R and dl will have an angle of 0. And that case, by Biot-Savart's law, the angle will be sine 0, which is giving you a 0. If the current that is being carried in the conductor and the point P are in opposite directions, so obviously between R and dl, the angle will be 180. And anyways, sine 180 is also 0. So irrespective of whether the point is on the left or the right side of a current carrying conductor on its axis, what you are going to get as the magnetic field will be 0. Okay. All right, let's move ahead. So here we have a question. Calculate the magnetic field due to the current carrying wire AB at a point P. So this is a current carrying wire AB and we have to calculate the magnetic field at this point. So very quickly what we have learned is P is equal to, this is a finite wire, mu naught by 4 pi, finite wire. The formula that we have learned here, I by A sine phi 1 plus sine phi 2 is applicable only to a finite wire. Okay. So here we have mu naught by 4 pi, mu naught by 4 pi, that is 10 raised to minus 7 into 10 raised to minus 7 into I, that is 2 amperes, into A, that is 10 meters. Okay, sine phi 1. So understand, this is sine phi 1 and yes, we have to take this angle. Bacha buddy, please don't get confused here. When we are referring to this formula, pay attention, we are talking about phi 1 and phi 2, which are angles here. When we are referring to Biot-Savart's law, we are referring to this angle. Okay, so the Biot-Savart's law, that is mu naught by 4 pi I dl sine theta upon r square, is actually referring to this theta. Here it is pi by 2 minus theta, but it is actually referring to this theta if it happens to be theta here. Okay, so but this derivation that we have done is referring to these two angles. Okay, the point that is making with the extreme ends. So here the point is making, so we are with pretty much a ready-made material of taking the angle consideration here. So this will be sine 45 plus sine 30. So this happens to be how much? This will be 2 into 10 raised to minus 8. Sine 45 gives you how much? 1 by under root 2. And this will be 1 by 2. So, and yes, there is a direction as well. Please pay attention here. So let's look at the direction. Here it is going like this. So it is going to go inside the paper. So the right answer would be D. The right option here would be D. Okay. So the right option D is the correct option. Are we clear on this one? Okay. Let's move ahead. Calculate the magnetic field due to all sides of the equilateral triangle at a point P. Okay, so they have missed out on mentioning that point P is basically the centroid. That's the case, it seems to be. Okay, we know that what is a centroid? A centroid is basically the intersection point of the medians. And when we talk about a median, obviously this, for an equilateral triangle, the median will be perpendicular. So if this happens to be, what is the length given? No length is given. Okay, but in all the answers we have L. So there are two things which are missing. This is P is centroid and this is length L. So if this happens to be, this is L, this is L, and this is obviously L by 2. This is obviously L by 2. If this is L by 2, then this length will be how much? L square minus L by 2 square under root. Pythagoras theorem, simple. So that will be L square minus L square by 4. That is 3L square by 4 under root, that is under root 3L by 2. So this will be under root 3L by 2. Now we know that the centroid divides the median in the ratio of 2 is to 1. So if we are talking about this length, I am talking, see, first let's calculate the distance of this point from this wire. So what will be the length? The length will be 1/3 of the total length. 1/3 of the total length. We see that the centroid divides the median in the ratio of 1 is to 2. So 1/3 means 1 by third into under root 3 by 2L. So that is going to give you how much? 1 by 2 under root 3L. This is 1 by 2 under root 3L. This distance will be how much? 1/3 of under root 3 by 2L. So this will be 1 by 2 under root 3L. This is the distance. Okay. So let's now calculate what is the magnetic field. So magnetic field will be mu naught by 4 pi. Mu naught by 4 pi. This is basically current I. This is current I, and this is the distance. This is the distance, that is 1 by 2 under root 3 into L. This is the distance. This is the current I by A, okay, into sine phi 1. Now understand, Bacha Party, we have to consider this is 90. Obviously, this will be bisecting it. So equilateral triangle has this as 30, this as 30. So obviously this angle will be 60 and so will this angle. Okay. So we can write sine phi 1 plus sine phi 2, that is sine 60 plus 60. Is it making sense? That will be equal to, so we are just first writing the formula, that is sine 60 plus sine 60. Okay, so the formula is mu naught by 4 pi I by A sine phi 1 plus sine phi 2. Okay, so this will be mu naught by 4 pi. This is going to go up, that is 2 under root 3 by L. Sine 60. Sine 60 will be how much? Under root 3 by 2. Under root 3 by 2. So that is going to be mu naught by 4 pi. This is 2 under root 3 into, this will also be 2 under root 3 by 2. This is L. So this 2 and this 2 gets cancelled. So this will be mu naught 2 into 3 by 4 pi L. So that is mu naught 4 pi, mu naught 4 pi 6L. Now understand, Bacha Party, mu naught I, I'm so sorry, mu naught I. mu naught I, mu naught I. Okay, 6 by L. Now understand, for this wire it is this way. Now understand, here the current is going like this. The current is going like this. So the magnetic field will be coming outside. Now in this wire also, obviously the magnetic field will remain the same because this distance will be same from the centroid. The centroid is basically a point in the equilateral triangle which is equidistant from all its sides. So this distance is also going to be the same that we have calculated here. Where is it gone? The same distance. So obviously the formula would be same. Now we have to just look at the direction. Here it's going like this. So obviously the magnetic field will be outside. In the same way, here it is going like this. So the magnetic field will be outside. So because of all the three line segments, or rather the direction of the current, the magnetic field is coming to be outside. Due to one wire, this is the magnetic field. So due to all three wires, this will be mu naught by 4 pi I 18 by L. So this will be mu naught by 4 pi 18 I by L. That is going to be the correcto option. Oh, no, 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 no. This is not the correct option. I am mistaking. This is outside. Yeah, outside is, sorry, outside is dot. Outside is dot. Yes, outside is dot. Here we have outside. Here we have outside, and here also we have outside. Okay. Yes, dot. All dots. So the net field will be. This is option C is the correct answer. The option C would be the correct answer. Okay. All right. That would be it from my end for today. Thank you so much for your patience and covering this up. Any questions, feel free to post it in the group or post it in the comment section, and we will continue further with live classes on this one. Okay. Thank you so much.